Okay, so the last thing we're going to talk about are fission chain reactions. Now, fission chain reactions, conceptually, it's not that difficult. Say you have a whole bunch of nuclei, right? All packed together, something like metallic uranium that we just discussed previously. So you have one neutron that comes in. It causes fission in one nuclei. That nuclei produces two neutrons, which then go on to hit two other nuclei to cause 4 fissions. Those 4 go out and hit more nuclei to cause 8 fissions, and then 16, and then 32, and 64, etc., etc. So the chain reaction is simply that we're causing something, a reaction, that itself goes on to cause more reactions on an ever-increasing scale. Now, one way to look at this is in the terms of something called the penny dilemma. And the penny dilemma is supposed to be one of those brain teaser things where you're put in a scenario and you're told you can have one of two things. You can either have $1 million or you can have a penny, which every single morning is doubled the amount of pennies that you have currently. So the first morning you'd have 1, the second morning 2, and then 4, and then 6, and then so on. Now, it's assumed that most people can't do or even visualize exponential math. And for the most part, this is true. I've been doing this for years, and I struggle to really make it conceptual in my head so that it makes sense. So most people would say, no, I'll take the $1 million. Who wants a bunch of pennies? Well, that exponential increase in the number makes it all worth the while. And I don't remember the exact number that it ends up being after 30 days. It's something like 10 or $100 million or some ridiculous figure. So let's take that ridiculous concept and let's go ahead and apply it to something like a chain reaction. So this all is based on exponential population growth. Now, in the case of the pennies, what we can say is we can write it out as a mathematical formula where we have the number of the multiplier for the increase that's happening, and then how many times is that occurring over this entire sequence. So say we are increasing the number of pennies we have by a factor of 2. So just like with normal exponents, you have a multiplier of 2 the first day, the second day, the third day, the fourth day. So if you multiplied all those together and used the exponential notation, you would end up with 2 to the 4th. So in that particular vein, say if we went out to, let's use something that's going to be useful in fission reactions. Let's say we go out and do this 50 times, 50 generations of penny doubling. What would that look like? Well, that would be 2, the first real generation of pennies that's been increased, times the number of occurrences where we double it. So that would be 2 to the 50th. Now, if we go ahead and do the math out on this, we end up with 10 to the 15th pennies. And that's a number that's so large, it has no conceptual reality for me. So 10 to the 6th is 1 million, 10 to the 9th is 1 billion, 10 to the 12th is 1 trillion. I don't even know what comes after that. I'm sure I'm going to look it up, but the reality of it is a number that's so big, it doesn't have any physical meaning. Well, let's try to give it some physical meaning. So I took the average weight of a penny, which is like a gram or so, and I said, let's multiply that by the entire number of pennies that we've generated, and let's see what the result is, because most of us can understand what mass is, in like kilograms. Well, it also turns out to be a number that doesn't really mean anything. It's 2.8 times 10 to the 12th kilograms. Again, there's nothing to even compare that to in your head. You don't know anything that weighs anything close to that. The best I could come up with that it's rather silly, but a rather apt comparison to show the difference in scale is a blue whale. Now, a blue whale, it's the largest, animal that's ever lived. And you would expect that it would be pretty big and have a lot of mass. Well, it does, but it's only about 1.5 times 10 to the 5th kilograms. This is 7 orders of magnitude less than the mass of pennies we have. So that little graphic where it shows a bunch of pennies filling a dumpster, that's probably not accurate. Now, the neutron growth in a chain reaction follows the same rules. It really does. So we're going to start with what some of our variables mean, where n is going to be the number of neutrons that we have, And little n is going to be the generation, or the step on this chain reaction increase that we're considering. F is going to be the number of neutrons created per fission, and L is going to be the number of neutrons that per fission that are useless. They escape, they're absorbed by something like uranium-238 or whatever happens to be there. For whatever reason, they escape. So in reality, you're getting 2 useful neutrons per fission per generation to sustain the chain reaction. And mathematically, we can write this out as the generation, which is n plus 1. So if we're in generation n, it's the next generation. We can take the number that we have, and then we multiply it by the total of the number of neutrons that we produce minus the number of neutrons that we lost, right? And this makes sense. If I start out, if my n is, we'll say 5, and I'm creating 3 neutrons but losing 2, that means the next generation I'm going to be able to create 10 neutrons, right? With me so far? Okay. Now, if we want to look at just the change in neutrons per generation, we can say that it's the next generation number of neutrons minus the current number of neutrons, right? So we know what we have, we know what we're going to get, and the delta, or the difference between them, is we just simply subtract them. Now, if we do a little algebraic manipulation and go ahead and do some substitution, we can end up with this expression that we have here, which is the number of neutrons in any generation is going to be multiplied by the number that we're gaining, the number that we're losing, and then we're going to subtract 1 because of math. Now, the next step is to say, all right, well, I've been talking about these generations as, it's multiplying here and here and here and making some sort of arbitrary divisions. Well, let's go ahead and actually make time a component of this process. So we have a delta n, which is the change in neutrons. Now let's go ahead and put in the amount of time that it takes for it to go from one generation to the next generation. And in this case, we're going to use our buddy unit, the shake, which is 10 to the minus 8 seconds, or 10 nanoseconds. So now we have a change in neutrons as a function of time using that cool little equation that we developed. Now we'll do a little bit of substitution here, because otherwise it's going to get a bit unwieldy to write all of these things over and over again. So we're going to say that the variable x is going to be equal to that f minus L minus 1 that we developed on the previous slide. Now what comes next? Well, we solve the differential equation. Call it magic or calculus, which is kind of what it is. We end up with a result that should look kind of familiar, which is the number of neutrons at any given time is equal to the number that we started out with and multiplied by an exponential, e raised to something. So what's e being raised to? It's being raised to this f minus L minus 1, or the change in numbers per generation, divided by the time of the generation. So we're going to make one last substitution, which is that alpha is equal to x over g. I know it's really wordy to say what's going on with these equations. Hopefully it's much easier for you guys just to look and see what's going on and it makes sense. Now, if we say that we're producing 3 neutrons and losing 1 per generation, which is the example I gave, we can say that it increases by a factor of 2, because 3 minus 1 is going to be equal to 2. So if we take that and then we go ahead and subtract a further 1, we end up with an x that is equal to 1. So that our alpha becomes 1 over g, right? Now, if we multiply that by the number of generations and the time that it takes for those generations to occur, which is ng, we end up with overall just n, the number of generations. Hopefully you're still with me. So now we can just take that and slap it back into that n equals n naught equation, and we end up with something that is almost directly identical to that penny dilemma that we derived, which is n, the number that we have at any given time, is simply going to be equal to the number that we started with, and then e raised to whatever generation that we're looking at. So each generation, as I said before, it only takes about 10 nanoseconds, right? One shake. Well, is that always true? Not really. If you're talking about nuclear power reactors, and this is in the lesson notes, if you're looking at nuclear power reactors, the average time between generations is much longer than that. It's about a millisecond. And you probably are asking, well, why are you talking about things in nanoseconds, but then when you talk about nuclear power, it's in milliseconds? Well, in nuclear power, the sustainment of the chain reaction relies on slowing those neutrons that are being produced down to a low enough level that they'll be readily absorbed by the uranium-235 that's in the fuel, or plutonium-239 in the case of MOX fuel. Whereas in a nuclear weapon, okay, we can't wait a millisecond, right? Because once this chain reaction starts moving, these neutrons aren't being slowed down by anything. So every successive generation is literally just taking those 10 nanoseconds. So you can think of a nuclear weapon kind of as a nuclear reactor. It's just one that operates very quickly and is sort of one-time use. Now, the energy distribution between something like a nuclear reactor and a nuclear weapon is also very different. A nuclear reactor has a huge volume of water that surrounds the fuel elements in order to carry away heat and then be transferred into power. A weapon doesn't have this luxury. It's basically metal and circuitry and whatever you can cram into the bomb that's going to not really cause any heat to go very far. So a nuclear reactor, that heat is spread over a very large volume, but in a weapon, it stays put. It's very concentrated, which is going to lead into what we'll talk about with the worksheet, is that you can only put so much energy into a finite volume before you just basically completely vaporize everything physically holding it together, and then it just starts expanding. So short time periods, a lot of energy deposition. You're looking at something they like to call energetic disassembly, or in layman's terms, it blew up. So if you looked at the course material for this lesson, there are the readings, there's the lecture notes, there's this lecture, and there's another file, an Excel file that's included there as well. And if you go through the lecture notes, basically tells you how to build this spreadsheet and ask you to do some things with it. I think I cut it off at 20 generations, so I want you sort of to extend it out and see how much energy you end up getting as those generations keep increasing. I also ask you to inject in this fission chain reaction a certain number of neutrons, of fusion neutrons, to see what effect that has, just doing it in one generation, what effect cumulatively that will have on the kiloton output, or the explosive output of the weapon. Now, here I've gone ahead and done it for, I think starting at, what did I start at? 48. I injected them in generation 48 and then brought it out to generation 58. Now, 58. Now, initially, when you do this, when you take and drag down without doing anything, the formulas, you'll find out that at generation 58, the output is approximately 100 kilotons. By injecting 10 to the 23rd neutrons in that 10 nanosecond generation, we've increased the yield of our weapon a ridiculous amount, from 100 kilotons to 3 megatons. So an entire order of magnitude, which occurred in approximately 100 nanoseconds. So what I want you to do is mess around with the worksheet, look at different times to inject, just for one generation, that 10 to the 23rd neutrons, and see what kind of effect it has on the overall yield. And, if you do it really early, how does that compare? If you do it 10 generations from the end or 5 generations from the end. I'm really curious to see what you guys think about how that exponential growth is affected by this injection. Now, the last thing I want to note is the limitations to energy released in a weapon by fission reactions. It's in the notes, so hopefully you've already read this, but the limitation is honestly dumping so much energy into such a small space in such a short amount of time, what ends up happening is, at the beginning, the thing that's holding, that fission chain reaction, that heat generation together, is basically the case of the weapon. And as you move from that fissile material, that uranium, as you start to consume it and deposit that heat, what ends up happening is you end up ionizing and literally vaporizing the internals of the weapon right up until, you can think of it as a heat front, reaches the outer portion of the case. And then it's going to very quickly ionize and turn into plasma, that outer case. Once that happens, there's nothing physically containing the expansion of that incredibly dense plasma that you've generated by fissioning all of that material. It will just start to go outwards, mostly spherically, and you will lose very rapidly that density that you had built up. And once you lose the density, that's when your fission chain reaction is going to stop. But that's all I wanted to do, and all I wanted to say about the worksheet. Please check it out, have fun with it, and we'll talk about it in the, I think we'll talk about it in the first webinar if you guys have had a chance to look at it. Otherwise, I may move this to the beginning of the second week's webinar, just to get your feedback and see what you thought about the exercise. So that's going to be it for me. We'll see you in the next lesson.